All right. Sounds like it's important. Yeah. Okay. So welcome to our first topology seminar this wonderful spring semester. We'll open it up with our own Craig's talk on Braids and Hopf algebras.
Thanks everyone for coming out, and thanks for the opportunity to speak. So let's see, and thanks for your patience with a Zoom talk. Sasha asked me a couple days ago if I could give a talk, and conveniently I had just given a talk in Zoom form, so I was like, sure, I'll just recycle the slides. In fact, I went so far as to not even recycle the slides, just cross out the previous talk and the previous date, and call the rest of it good. Right. So this is a sort of topology specific, sort of colloquium level talk, and so please just feel free to jump in with any questions at any point. Let's see, let me actually make the chat visible so that you can of course ask the questions in the chat. Right, so my plan is to talk a bit about the sort of classical theory of Hopf algebras, and then start talking about braided categories, braided monoidal categories for a little bit, and then which will lead us to the main definition of the talk of braided Hopf algebras. And then a question which has been hanging for some time of like how to understand the structure theory of braided Hopf algebras. And my goal is to try to get to some sort of analog of an answer which would be a version of the Milner-Moore theorem for braided Hopf algebras. Right, and along the way we'll talk a bit about braided operads, and you will all be sick of braids by the end of the talk. I also want to take a moment to acknowledge the very recent passing of Fred Cohen, whose work in operads and configuration spaces and braid groups has very substantially impacted how I think about mathematics in general, but in particular about the math that's going on in this talk. So if any of you are on the AlgTop listserv, you'll see that he was a very beloved person based on the outpouring of emotion that's gone on in the last couple of weeks. Anyhow, it certainly is material that I learned that has informed my thinking about this math. So right. Anyhow, so let's talk about Hopf algebras. Right, it's a algebraic topology talk, so it wouldn't feel right to not start with a definition that takes up half a page. A Hopf algebra, let me remind you, is going to be, we're going to focus on Hopf algebras over fields K. Hopf algebra is a vector space A over K with maps that of the form mu, which goes from A tensor A to A, and delta in the opposite direction. There's also, so mu is called the multiplication, delta is the co-multiplication or co-product or diagonal. S is called the antipode. Epsilon from A to the ground field is the augmentation. Eta from the ground field to A is called the unit, and we'll often confuse eta with the image of the element 1 in K under this map, which is then an element of A. And the reason we want to call it 1 is that collectively the structure of the Hopf algebra, the multiplication, and the unit give me a unital associative algebra. That's our first axiom. The second axiom is dual to that if I take the dual objects, the algebra, the diagonal, and the co-unit or augmentation is a co-unit, co-unital co-associative co-algebra, which is something that is perhaps easier to write down in terms of diagrams than in terms of formulas as to what that exactly means. The third and maybe most important and subtle assumption is that the diagonal is a homomorphism of rings or of k-algebras, and the product is a homomorphism of co-algebras. And then there's a couple more assumptions which I really don't want to dwell on here, that epsilon splits eta, and then this is sort of saying that S serves as a inverse to the identity in convolution on the Hopf algebra, but I'm not going to fuss too much about this. I really mostly want you to focus on these first three requirements, which are, I guess, along with this as well, gives me the definition of a bi-algebra. And really, you can sort of ignore the antipode for most everything that we're going to be talking about here. Right, so, but, and even more, I urge you less to focus on the definitions and more on the examples. So our favorite examples, I've got three, and there's two here, and then the third will come along in a moment. The first is the group ring of groups. So I take the vector space. This is the direct sum over elements of G of a line through G, which, let's see, maybe I'll just say K on G. This is a Hopf algebra where the multiplication is induced by multiplication in the group. The unit is the image of the unit in the group times one in the field. The antipode is induced by inversion in the group, sending a group element to its inverse. And then the coproduct, the diagonal is interesting here. The diagonal of each element of the group is the group element tensored with itself. So this is, you're just repeating elements of the group. And if you have an element in a Hopf algebra for which this formula is true, that element is said to be group-like, which is a term that's going to come up in a little bit. And then finally, the co-unit or augmentation, just if you take a formal sum of elements in G, it just strips off the elements of G and just sums the numbers that we're decorating it. So that's the structure of the Hopf algebra on the group ring. There's a very similar construction if you replace the group, if you ask further that it's not just a discrete group, but a topological group. You can take the homology of the group with coefficients in your field K, and this also becomes a Hopf algebra, and almost like word for word, everything is induced by the corresponding constructions in the group itself, the multiplication in the group, the diagonal of the group in terms of the category of spaces induces the diagonal on the Hopf algebra, and so on. Right, so I should say this Pontryagin ring is really was maybe one of the real focus of algebraic topology in the sort of heroic era of the mid 20th century. In the work of people like Borel and Cartan and Hopf, for whom these algebras are named, spent a lot of time figuring out the homology of Lie groups for the most part, and then closely related questions about the Steenrod algebra, which is also a Hopf algebra. That's the topology community is maybe certainly took the notion of a Hopf algebra and ran with it in that period of time. But shortly after that, the algebra community continued working with Hopf algebras in a more purely algebraic context, and we'll encounter some of those in a moment. Well, let me see, before I go ahead, does anybody have any questions? Cool. All right. So to an algebra, we can associate, to an associative algebra, we can associate another object, which is a Lie algebra. So let me just remind you that a Lie algebra is a vector space, again, over the same field K. And it's equipped with an operation we'll call a bracket. It's a binary operation. It's required to be anti-symmetric. I guess in characteristic 2, it's not anti-symmetric, it's that the bracket of something with itself is 0, which is a little bit stronger than being anti-symmetric. And it's supposed to satisfy the Jacobi relation, which is you take the bracket of A with the bracket of B with C, and then cyclically permute those terms and add them up, and you're supposed to get 0. And our favorite way of producing this such a Lie algebra is by taking an associative algebra, and then we can regard it as a Lie algebra where the bracket of A and B is the difference of A times B and B times A. Of course, this is a sort of forgetful operation. You've forgotten some of the structure of the associative algebra, but all of the multiplication, and just remembered this little bit of the multiplication. And you of course lose a lot of information. So if, for instance, if A is commutative, then the corresponding Lie algebra is said to be abelian, meaning that the brackets are identically 0, right? Because then A times B is equal to B times A. All right, so that's one way of producing a Lie algebra from an algebra. But if your algebra is further a Hopf algebra, there's another way of producing that, and that's by taking a subspace of the Hopf algebra called the primitives. So the primitives are the elements of the Hopf algebra where the diagonal takes the following form. It's the diagonal of A is A tensor 1 plus 1 tensor A. So they are, in some sense, along with the group-like elements, they're the simplest elements to the eyes of the coalgebra structure. And it turns out that the primitives form a sub-Lie algebra of A, where here I'm sort of equipping it with this bracket, the A times B minus B times A bracket. And let me, so I want to do the proof. It's really easy, but there's a point where it's going to fail in a more general setting. And I want to draw your attention to that. So, right. So here's the bracket of A with B, and then I take the diagonal of it, and so it's the bracket of the diagonal of A times B minus B times A. Now, one of our assumptions was that the diagonal is a ring homomorphism. So I can do that by taking the diagonal of A, diagonal of B, diagonal of B, diagonal of A, multiplying them, taking their difference. And A and B were assumed to be primitive. So that's A tensor 1 plus 1 tensor A, B tensor 1 plus 1 tensor B, and then the difference in the opposite order. And then I have to multiply these things together. And I'm doing multiplication in A tensor A. What does that mean? That means you take, if I want to say, multiply this term by this term, I take the first term in each thing and multiply them together, and that gives me the AB. And I take the second thing in each term and multiply them together, and that gives me the 1. Right. And if I do that elsewhere, so for instance, like I got this green term A tensor B by multiplying this with this, because A times 1 is A and 1 times B is B. And then there's an interesting one, which is multiplying 1 tensor A with B tensor 1. That's going to give me B tensor A because I've got to move the B past the A and multiply both of them by 1. In any case, you do that for all, 8 products, and you see that you have an occurrence of A tensor B, and another occurrence of A tensor B, and an occurrence of B tensor A, and another occurrence of B tensor A, but on opposite sides of the negative sign, so they cancel, cross terms disappear, and you're left with just the bracket tensor 1 plus 1 tensor the bracket. Right. So primitives in Hopf algebra form a Lie algebra. Questions about that?
Craig, one of your basic examples was the homology algebra of a topological group, and it seems to be a graded Hopf algebra.
Yeah.
And so here you would also, you would have to insert signs, but miraculously everything will go through. Right?
Yeah, I am suppressing the signs here, and one should not. So yeah, that is certainly something that one needs to be certainly very careful about. And indeed, that calls into question what we mean by the word anti-symmetric. We really mean some sort of graded version of anti-symmetric, which could actually mean symmetric when applied to odd dimensional things. So yeah, there's plenty of subtleties when applied in the graded setting. Other questions? All right, so that's how to extract a Lie algebra from a Hopf algebra. And you can reverse this procedure. From a Lie algebra, you can produce a Hopf algebra. And this is going to be the third example that I want us to focus on, which is the universal enveloping algebra. So if L is a Lie algebra, not necessarily the primitives of the Hopf algebra, then the universal enveloping algebra is the free associative algebra on L, modulo a relation which says, this is equipped with some bracket here, and I just make that bracket equal to the bracket that we were talking about in the previous slide, the AB minus BA. Here, the free associative algebra is also usually called the tensor algebra, and it can be written down as follows. You just add up all, oops, that's supposed to be a plus. You add up all finite tensor powers of your vector space, and then multiplication is formal. So like if I want to multiply something in here by something in here, it's just concatenate the two tensors and put it in there. So that's the way in which it's a free algebra. But this turns out to be a Hopf algebra by extending the following formulas on L multiplicatively. You make L primitive, and then the antipode is just negation on L, and then the co-unit is 0 on L. Right. So just to, if you want to space out at this point, convince yourselves that these do in fact satisfy all of the axioms, but maybe not the most fun. Some special examples of this, if I take the free Lie algebra on a vector space, so I take the vector space and I join formal symbols like the bracket of A and B, and then the brackets of brackets, and so on and so on, as long as they're anti-symmetric and satisfy the Jacobi relation, I get something called the free Lie algebra on V. And if I take its universal enveloping algebra, I get the tensor algebra on V. So, and this statement is sort of dumb. This is kind of, both of these things have the same universal property about maps from V to some algebra. That's a proof that they're the same. So it's this construction, except that there's sort of no relations here. At the other end of the spectrum, if my Lie algebra, rather than having as many brackets as possible, it has no brackets. If I have an abelian Lie algebra, then the enveloping algebra is the symmetric algebra, or if following Sasha, I'm working in a graded setting, maybe it's the graded symmetric or exterior algebra on L. So what am I doing? I'm taking the tensor algebra on L, and I'm modding out by the ideal AB minus BA is equal to 0, because this is now 0. And that's precisely I've made everything commute. So it's the free commutative algebra on L. All right. So these two operations of going from Lie algebras to, Hopf algebras to Lie algebras by taking primitives and back by taking enveloping algebras turn out to be inverse to each other, and in fact an equivalence of categories in a certain setting. So this is the theorem of Milner and Moore. This is one version of the theorem of Milner and Moore. If I'm working over a field K of characteristic 0, And if A is primitively generated, that is just as an algebra, it is generated by its primitives. If it's a primitively generated Hopf algebra, there's a natural map from the enveloping algebra to A, which is induced by the, so P of A, I just include P of A into A as the primitives, as a subspace of primitives. And then the enveloping algebra has the universal property of like every map from a Lie algebra to an algebra extends over the enveloping algebra to an algebra homomorphism in a unique way. So I get a natural map from the enveloping algebra to A, and this map is an isomorphism of Hopf algebras. So let's just pause to point out that the assumption that it's primitively generated is the same thing as saying this map is surjective, right? That this is sort of the free thing generated by the primitives. And as long as the map is well defined, it will therefore surject onto the subalgebra generated by the primitives, but that's everything. The content of the theorem is that it's also injective. And their proof uses the Poincaré-Birkhoff theorem. I should say there's also a version in characteristic P, which involves the use of restricted Lie algebras as well. But I'm not going to focus too much on that here. But it has a similar statement. There's where you use restricted Lie algebras and enveloping algebras of restricted Lie algebras. Questions about the statement of the Milner-Moore theorem? So I'm not entirely sure about the attribution here. There's an extension which it is got to be due to some subset, probably the whole set of Milner, Moore, Cartier, Gabriel, and Constant. So I think the history is that this was unpublished work of Constant that simultaneously I thought just Cartier had done, but if you look at Cartier's book on Hopf algebras, he refers to himself and Gabriel. So I'm just going to go with all 5 of these people. So you can extend the Milner-Moore theorem to say that if you're working in the setting that K is an algebraically closed field of characteristic 0, and if A is just co-commutative, that's our only assumption, then the Hopf algebra can be identified as a sort of semi-direct product. This is really as a vector space and as an algebra. This is really the universal enveloping algebra of P of A tensored with the group ring on G of A, where G of A is the group of group-like elements. And then the group-like elements act on the primitives by conjugation, because I'm allowed to invert things in group-like elements. And so there's actually some sort of twisting going on there. And that's the Cartier-Gabriel-Constant theorem. I should say that the assumption of being algebraically closed here is used to ensure that this is a group ring. If it's not algebraically closed, I think you can still decompose it as a twisted tensor product of the co-radical along with something like an enveloping algebra, but just to ensure that the co-radical is a group ring, you need the algebraically closed condition. So anyway, I'm probably going into more detail than anyone wants to hear. Let me pause again and see if there are any questions.
Yeah, I have a quick one if you can hear me. Should it be obvious to me why the group-like elements form a group?
No. I mean, it's a little bit of work. So the multiplication is the multiplication in the Hopf algebra. Then you have to convince yourself that the product of 2 group likes remains group like. So that would establish that it's a monoid. But then the inversion the inverse of a group-like element. So G inverse is going to be computed as S of G, where S is the antipode. And then you have to take a moment to convince yourself that indeed, I think it's where was it? Like this is going to show that S of G is a left inverse, and this is going to show that it's a right inverse. Yeah, cool. Other questions? All right, so let's talk about braided monoidal categories. Right, so I absolutely want to suppress a lot of the details in this definition, because you could spend the entire talk talking about braided monoidal categories. But a category is said to be monoidal if we have a bifunctor from C cross C to C, so pairs of objects and pairs of morphisms produce single object and morphism, along with an object called 1 in C, which make C something like a monoid in the category of categories. That's a little bit awkward, because the category of categories is a 2 category, and so the monoid is in some sense only up to some sort of naturalized morphisms, and dealing with that statement is a bunch of axioms about coherences that I am not going to spell out here. But you have, in particular, an isomorphism of A tensor B tensor C to A tensor B tensor C in the 2 different parenthesizations of that. That's the associativity. And 1 tensor A is isomorphic to A, and vice versa, and the same on the other side. We'll focus on braided monoidal categories. They're ones where there's a natural isomorphism from A tensor B to B tensor A, which satisfies some axioms, which I'm also not going to talk about for the most part. But that the category is further said to be braided if is further said to be symmetric if the braiding squares to the identity on A tensor B for every A and B. So you know a bunch of examples of symmetric monoidal categories. The category of sets, the category of topological spaces. Both of them have a monoidal structure where the tensor product is just the cross product of sets or topological spaces. Category of vector spaces, along with the tensor product, is a monoidal category, and they're all symmetric monoidal. The braiding here this is the formula on vector spaces. On sets, it's sigma of A comma B is B comma A. And if I do that twice, indeed, I get back to the identity on A cross B. So these are in some sense not the point of this talk. A very good example of a non-trivially braided monoidal category is the category of Jeter-Drinfeld modules. So if G is a group, YDGG is the category of right G modules, V, which furthermore can be written as a direct sum of subspaces, V sub G, indexed over the group, with the property that the right action by an element H in my group on VG puts it into VG conjugated by H, right conjugated by H. So that's a thing. It arises more often than you would think. But the tensor product of 2 such things is done the way that you know how to take tensor products of things. You take, right, I mean, it's a vector space. You take the tensor product of V with W over your field K. But I have to tell you how to decompose that into a direct sum. And then the way that I do that is say, well, the G indexed part is going to be the sum over VH tensored with W H inverse times G. That's times and not conjugated by. And you should remember this, that like H times H inverse times G is G. So really this is just like adding up over, it's like in a normal graded tensor product of graded vector spaces. The stuff in degree n is the is the sum of p plus q equal the sum over p plus q equals n of vp tensor wq. It's the sort of non-abelian version of that construction. But what's interesting is that the braiding is non-trivial. The braiding is given by saying, well, indeed, I'm going to move v past w. The w moves into the left slot, but the right slot, v gets acted on by the element h that that labels the component that w lives in. So there's the group action gets intertwined in with the braiding. And you can just convince yourself if I sigma it again, I get to v times h tensor w times, well, I guess I act by gh, because now this is in degree gh, or this is, I mean, the v is in the left and the w is in the right, so that is sort of where we started, but they've been acted upon by the group, and so unless the group is trivial, that doesn't need to be the identity. So a very simple example of the Jeter-Drinfeld module is just the group ring, where the sum end labeled by G is the line through G, and the right action is just conjugation. Let me pause and see if anyone has any questions.
Craig, is it really G times H? Shouldn't it be G to the power H?
Possibly. Let's see. So you ended up.
Because
yes, you're absolutely right.
Because V times H is in degree G to the power H. Okay.
Thank you.
Just wanted to make sure if I'm with you. Okay, great.
Right. So, okay. Right. So why are these called braided monoidal categories? So one of the axioms which I suppressed was the following one, so that there is an equality of maps from A tensor B tensor C to C tensor B tensor A, which is of the form this: if I do the braiding on A tensor, sorry, composition that starts on the right. If I do the braiding of A tensor B and leave C alone, and then braid the second and third and leave the first alone, and then braid the first and second and leave the third alone, that's the same as doing it in the other order. First braid the second and third, then the first and second, then the second and third. So that's one of the axioms. And you can draw it pictorially by saying first braid the first and the first and second, then braid the second and third, then braid the first and second. That's the same thing as braiding the second and third, the first and second, and the second and third. And these are pictures inside of the third braid group. Right, so B3 looks like the third braid group involves pictures like these and multiplication, like by stacking braids on top of each other. This equality is true in the braid group, right? Like if I look at these strands here, I can straighten this one out to be this. I can bump this little guy over into the middle into a straight line, and I can straighten out the one in the back to one going through the back like that. And I can do the same thing on the other side. I can straighten each of these things out and get the same picture, so the two braids are the same. So that is an equality in the braid group. So what is the braid group again? I mean, it's, you know, the isotopy classes of pictures like this. It's generated by, it has this abstract presentation that that Artin found, where it's generated by sigma 1 through sigma n minus 1. Here, sigma I is the following braid. I do nothing for the first I minus 1 strands. I braid the ith and I plus first strands, and I leave the rest of it alone. And two braids, two of these generators commute if they're not right next to each other. So if I minus j is bigger than 1. They satisfy this relation sigma I plus 1, sigma I is sigma I plus 1, sigma I plus 1, if they are right next to each other. And notice that this is just an index form of this relation. So really what that tells me is that if I try to form an action of the nth braid group on the n-fold tensor product of something in my category, where sigma I corresponds to doing the braiding of the ith and I plus first tensor factors, that gives a well-defined action, because indeed, if I do a sigma here and a sigma somewhere over there, they commute. But if I do sigmas right next to each other, they fail to commute according to this formula up here at the top, which is part of the presentation of the braid group. So life is good. All right. We can save this for later, but I'll say that A is finitely braided if this action of Bn factors through a finite quotient of Bn. And the structure of a braided category has a wonderful consequence, which is that if I have two algebras in my braided category, then their tensor product becomes another algebra in my category. And how do I do this? If I want to multiply something in A tensor B with another thing in A tensor B, what I can do is first apply the braiding to swap the B and A. So I've got the A and A side by side and the B and B side by side. And then I can apply the multiplication in A, followed on the one and the multiplication of B on the other. And that gives me something in A tensor B. And that's my multiplication on A tensor B. In some sense, this is the minimal amount of assumption that you can make in order for the tensor product of two algebras to be an algebra. All right. Okay, so let's see. So the new definition I want to focus on is that of it's not that new, but maybe new to us, is that of a braided Hopf algebra. So this is a Hopf algebra object in a braided monoidal category. And that sounds like cheating, and it kind of is, but it's exactly the same definition. The definition is all about, it's all written down in terms of objects in my category and morphisms in my category, where now I'm interpreting the tensor product as in my monoidal structure in my braided monoidal category. And K is now the unit of my category, and so on. But I want to focus on something important, that this assumption that delta is an algebra homomorphism is still true, that this map is supposed to be an algebra homomorphism, but the target now is given a different multiplication than what we were talking about before, of like just multiply the first two terms together and then the second two terms together. It uses this multiplication. It says first do the braiding of A past B and then multiply two things together. So that's the main novelty, is that the diagonal is assumed to be an algebra homomorphism where A tensor A has this new multiplication that involves the braiding in my category. And that messes everything up. So maybe just for sake of time, I won't necessarily spend too much time with the examples. There's a very rich theory of examples here. There's this Fomin-Kirillov algebra arises in combinatorics and representation theory. It's home to a sort of non-commutative form of Schubert calculus. And you can ask all of the sort of questions that you ask in Schubert calculus there, like, the things like the non-negativity conjecture, or for the structure constants, for the Littlewood-Richardson rule, and things like that. But this is a Hopf algebra in the category of Jeder-Drinfeld modulus for the symmetric group. And then these objects sort of appeared in the Hopf algebra community quite a long time ago. So let me sort of reverse let me do the following construction. If I have a Hopf algebra in YDGG, then I can do the same sort of construction that I was doing in the definition of in the statement of the Cartier-Gabriel-Constant-Milner-Moore theorem, where I twist my Hopf algebra, my braided Hopf algebra, by the group ring. And it turns out that that construction, Radford proved, actually produces a normal Hopf algebra. Hopf algebra just in the category of vector spaces over K. So there's a very ambitious program of that was begun by Andruszkiewicz and Schneider, which said, hey, let's try to reverse this procedure. If I want to try to classify finite dimensional Hopf algebras, and they're assumed to be pointed, which is that the basically that the co-radical of the Hopf algebra is a group ring. But let's not worry about that. But the idea was, I want to classify finite dimensional pointed Hopf algebras by saying, let me try to take an arbitrary Hopf algebra and reverse this procedure, try to identify it as a Radford byproduct of a group ring with a braided Hopf algebra, and then try to go and classify all of the braided Hopf algebras, which when you say it like that, that sounds crazy, because that's not a reasonable task. But it's unbelievable how effective that program has been. Right, so those are some occurrences of braided Hopf algebras, and I think a bunch of you have listened to me talk about them, so you don't need to hear why I think they're cool. All right, so finally, I want to get to the question that I probably should have gotten to a while ago, which is, can we play the same game as in the Milner-Moore theorem for braided Hopf algebras? So if A is a braided Hopf algebra, what structure do its primitives possess? And the problem is it's not a Lie algebra any longer. So if we walk through the same proof that we had before, everything works fine until I start to actually multiply things. So when I multiply the A tensor 1 with the 1 tensor B, indeed I do get A tensor B, because what am I doing? I'm braiding 1 past A and 1 past 1, right? And that's 1 is in the trivial component, so nothing is actually happening there. But if I wanted to multiply, for instance, 1 tensor A with B tensor 1, I have to braid the B past the A, and that gives me this. And then similarly on the other side, I get a B tensor A and a sigma of B tensor A. And now it's now not clear any longer that these two things are going to cancel in pairs, because they're just not obviously the same thing any longer. I mean, they will be the same thing if indeed sigma of A tensor B is B tensor A and vice versa, they'll cancel as they did before. So it's not a Lie algebra any longer. You can ask, what is it? And I don't know. But this is about a sort of partial answer to what it is. So one of the things it does have is, like, if you sort of just keep going, if you add twists and twists and twists and twists of A tensor B under the assumption that eventually you get back to the identity by twisting, or maybe with sign, if it has finite order, you can add up the twists and multiply them together with signs and divide by n just to make some consistency. Then this operation, you can check that this not argument eventually shows that this is a primitive once again. And it's sort of a version of the Lie bracket, because indeed, if sigma of A tensor B is B tensor A, then the order of minus sigma is 2, and I'm really just getting the bracket of A with B, or half of the bracket of A with B. So this is some kind of generalization of the Lie bracket. And you could ask, what is the Jacobi relation for this funny new bracket or brace? And I don't have a very easy answer for you, I'm afraid. So that's part of the story. The right way, in my mind, to frame this question is in terms of the language of operads. And so I think a bunch of you are familiar with it, so I'll breeze through it. An operad is a gadget which encodes algebraic structures on, in this case, braided objects in braided monoidal categories, where the algebraic structure is encoded by an n-area operation or a collection of n-area operations. So we've got a tautological example of the endomorphism operad, whose nth term is the Hom in the category from A tensor n to A. This is tautologically the space of n-area operations on A. And what do we see about it? We've got a Bn action because Bn acts here, since I'm in my braided category. And then we've got structure maps about like composing n-area operations with m-area operations, where I put the m-area operation in the middle m terms of my input, I apply them there, and then just the output is a singleton. I just put that in that one spot, and then I can apply my n-area operation to that and get an n plus m minus 1 area operation. And then these satisfy various axioms, which are not fun to write down. The abstract notion of an operad abstracts these properties in the same way that a group abstracts its notion of a representation. But an instantiation of an operad is an algebra. That's a map of operads from O to the endomorphism operad of some object A, much in the same way that a representation is a group homomorphism from G to GL of V. But in particular, if this means that each element of ON produces an n-area operation on A. All right. So maybe I will skip the examples because I think most of you are pretty familiar with the examples. Right, so our favorite example in topology is the little disks operad. Let me just remind you that the two-dimensional little disks operad, the spaces in the two-dimensional little disks operad are homotypically equivalent to the configuration spaces, the ordered configuration spaces of endpoints in the plane. And those spaces have the braid group or the pure braid group as their fundamental group. Now, Fred proved as part of his thesis that the top part of the homology of E2 of n forms an operad, and that operad is isomorphic to the Lie operad. And I might be, Sasha, do I need to actually say it's the suspension of the Lie operad? Or is it actually the Lie operad? I think you're muted.
Okay, sorry. Yeah, I think you're right. I think it's the suspension of the Lie.
Yeah, okay. All right. Yeah, sorry. Okay. But this is a highlight that I just want to point out that the thing that was working for the primitives in a normal Hopf algebra is the top homology of the little disks operad. Up to some suspension that I'm a little confused about. So the theorem that maybe the results that I want to just sort of end with is the following. So if I look at the set, or really the inverse system of finite sheeted regular covers of the nth space of the little disks operad, well, those are indexed by finite index subgroups of the nth braid group. So these are things of the sort K n1, where n is a normal finite index subgroup of Bn. And that forms an inverse system. And it turns out that that inverse system collects together into a braided operad, braided because now the braid group is acting through deck transformations on these guys. It's acting through its quotient of the finite group Bm mod m, but that's all right. We've got the, so the braid groups act on the finite shaded covers, and collectively they form a braided operad in the category of inverse system of space and prospaces. We can take the top homology as before, and I'm going to call that, so that's going to be an inverse system of vector spaces. That forms an operad of pro-vector spaces now. And I'll call that the braided primitive operad. So if we work in characteristic 0, we can prove that if A is a finitely braided Hopf algebra, then its primitives are an algebra over this operad Bur prim. And not in a dumb way, the free objects are correct. That is, just as before, the primitives in the tensor algebra on a finitely braided vector space V is the free Bur prim algebra on V. And so this is the sort of statement, this is the braided version of the statement that we were saying before, that the primitives in the tensor algebra are the free Lie algebra on V. This is a braided version of that statement. So you could ask, okay, but like, what is this? In particular, you might hope that it is generated by this brace that we drew, that we described last time, just as the Lie operad is certainly generated by the bracket. And unfortunately, that's not true. So something that Callista and I have found fairly recently is that there is, if you look at the sort of minimal set of generators of the operad Bur prim as a braided operad, it has a new generator in every arity greater than or equal to 2. So the generator in degree 2 is indeed this bracket, but there's a 3-area operation that is not a composite of brackets. There's a 4-area operation which is not a composite of brackets or a composite of them with this 3-area operation. We would very much like to understand what those things are, and that's an ongoing project. But I think I've talked too much already, so maybe I'll stop here. Thank you.
Okay, let's thank Craig for a very interesting talk. Any questions?
Could I ask, Craig, thank you for all this stuff. And so I'm probably not going to understand your answer, but maybe there is some aspect because it gets into technicalities, but you've got in this theorem of yours, you've got that A is a finitely braided Hopf algebra, which means that it factors through a finite quotient to the braid group, right? As I recall. And also you're requiring that the characteristic of K is 0, which is a condition which occurred in other places. But where on earth in all this is the fact that you've got a finite group coming? Because I would have thought it ought to work in generality. I can't see any finite group around the place.
I think it is probably true that this first statement is true in all characteristics, but the second statement is not. What this is allowing me to do when I take the free algebra over this operad on a braided vector space V, wait, so were you asking about the finite, where do we need the finiteness of the group, or where
Yeah,
do we?
why would you need finite? The whole thing works like everything is working in generality. You know, you've got like categories and stuff like this all over the place.
Sure.
And the moment we're working in that sort of generality, I would have thought that anything you prove might work in some generality like that. I can't see why you would want a finite group.
Yeah. So if I have a braided operand and an arbitrary object in a braided category, the free algebra, which I'll write as O of V, is the sum over n of O of n tensor over the braid group with V tensor to the n. Where the braiding here is by definition, and the braiding here is by the fact that it's in a braided category. Now, here's the thing: if I get to assume that the braid group, the action of Bn on V tensor to the n factors through a finite quotient, I can rewrite that as the sum over n on, take the co-invariance under this normal on the one factor, and then tensor over the, let's call Q the quotient with V tensor to the n. And now, so what does that do? That tells me this thing, the right thing to study these finitely braided guys is indeed this inverse system of finite sheeted covers, or the sort of profinite completion of this gadget. It also means that when I'm working in characteristic 0, tensor, I mean, since K is flat over KQ, a lot of I never have to take group homology. A lot of exact sequences stay exact. I mean, there's a lot of things that just work right when I'm in that setting. There's some of this which could be relaxed, but let me just point out, I mean, this statement doesn't actually make sense for infinitely braided Hopf algebras, because the isotropy of every term in this inverse system is through a finite quotient. So if your action is not through a finite quotient, there is no way that you could even talk about this being a Bergkrem algebra. I have another answer, which is
Craig,
less compelling, which is that the
Craig, I'm sorry, before you start giving another answer,
yes.
I apologize because I have to run to teach a calculus class in 5 minutes in a different building. So, but I'm entering this conversation because I'm host. So can I transfer host into you? I will stop the recording right now.
Go for it.